Hi everyone, can you hear me? Yes, we can get started. Just checking if you can hear me.
Yes, can hear Dr.
Okay, thank you, Rasman. Okay, thank you, Felix. Right, today we're going to review just briefly some of the key concepts on process variability. There is pending test one coming up. We haven't set the date yet because you asked for a postponement, but I will take a poll very soon on WhatsApp. And then, of course, your tutorial 1 and 2 has been postponed, but probably due in the coming weeks. This topic for tonight, the just general discussion, is part of the third important theme. There are four important theme or topics in VLSI. The first is to know the process flow, how ICs are designed all the way from RTL right down to the geometry level. The second, we talked about it the last time, a little bit how to estimate the critical path, how to do estimation of delay using logical effort. So if any of these things you have questions, just feel free to interrupt me. But if not, I like to actually go straight into the material for today's discussion. We'll be talking about process variation, variability. Basically, the key idea, this is one of the main limitations of modern VLSI design. The variability itself is really challenging. And I don't really see that we can do such a great job of tightening the variability. One of the reasons is because we are actually really just making really, really small devices. Each transistor, each logic gate is going to be really, really small. Right now, I think the state-of-the-art process technology is 3 nanometers. That means the gate length is roughly on the order of 3 nanometers. Of course, it's folded up like a FinFET structure to get it a bit longer, but you know the device size is 3 nanometers, and you're actually down to several molecules type of dimension, because molecules tend to have dimension in the order of angstroms, which is 0.1 nanometer. That range of size is what molecules are, right? So you're down to the level of just a few molecules per device. So it's going to be pretty difficult to really control very precisely what we can fabricate. So process variability is going to be here to stay with us. But what's helpful is we try to understand, try to put some estimates around process variability, try to understand how it affects the design, and then we over design for that. So the key here is basically to over design and to build in some safety, some additional uh, intelligence into our design so that we can counteract, or we can actually not be so susceptible to the variability. Okay, when you talk about process variability, we know that there are sort of three general uh, uh, phenomena or environments that can cause variation in the performance of our VLSI IC. Okay, so when we talk about variability, it's more like saying that I have one design. I've already done a good job of characterizing my design, simulating it. If I can make it, that'll be great, right? I know its speed. We've went through last time, looking at the max delay, mean delay constraint, clock skew, and all that. So I've created my design. I know how well it will perform. I know how well it's estimated, provided I can make it as I want it, right? So that's in the direction, the domain of process variation. So if I'm not able to make the design exactly like I want to, so like I try to draw a straight line, but maybe I have some variation in the width of I don't exactly get it right. right? Or if I want to dope a certain concentration, 10 to the power of 5 atoms per meter cube or something like that. But then, I'm off by a couple of atoms or something like that, right? So I'm not quite there. That can actually change the performance of the individual transistors. That can actually change the performance of individual logic gates. So there are going to be slight changes, and these process variations, they tend to add up. Okay, so process variations, that is when I try to make something according to a recipe, according to a design, my imprecision, the inability of my fabrication process to make exactly the same thing is going to cause variations between each chip that I make. Okay. Besides that, how I operate that VLSI IC, right? So I've already created it, fabricated it, I cut it up, I put the wires, wire bond it, and then I'm running it, right? So if I were to operate this IC at maybe VCC versus 5% higher of VCC or 5% lower VCC, so variation in the supply voltage itself will also cause variation in the expected performance of the chip and variation in the operating temperature as well. So if I operate the chip, the IC in maybe the Antarctica, right, where temperatures are 0 degrees or sub-zero, like minus something, versus I operate it in Malaysia, where the temperatures are like 30 degrees, 35 degrees, versus maybe I operate it maybe in an oven or something like that, where it's like 100, 200 degrees, or maybe in some industrial furnace or something where it's 200, 300 degrees Celsius. The performance will be different because temperature actually influences things like the carrier mobility, number of free carriers, and things like that. Survive voltage influences the amount of strength, amount of current that is driving. So when we want to look at variability, like how does the chip perform under this variation in manufacturing, process variation, and variation in operating environment, the supply voltage, the temperature. This, we call it the PVT variation, process, voltage, and temperature. And usually your design, you don't just simulate it at the desired point. You would simulate it at what we call corners, the PVT design corners, right? So the design corners basically are telling you, you're just taking a view of how your design would change in terms of its performance under the corners. So conventionally, there are like 5 alphabets. So the alphabets can take on either F, T, or S. T means typical, that means that's what you design it for. S means slow corner, and there's a certain definition of slow. And F means fast corner. So slow corner, fast corner. So if you're talking about NMOS and PMOS, these are process variation. That means variation in the way you manufacture the NMOS such that they become slow devices. That means maybe things like the VTH becomes a little bit higher than intended. So your current is not as strong, right? Or you are doping the NMOS less than intended. So then there's less free carrier. So the current is not as strong. So it tends to be slower. Or fast corner means it's the opposite, where the doping is maybe higher or the threshold voltage actually lower. And the same for PMOS, right? You have a slow corner, a fast corner. And also for wires, you have a slow corner for wires, fast corner for wires. And VDD, the fast corner is when you actually have 10% higher than the nominal voltage. So nominal voltage is the voltage at which your process is supposed to run. So like, let's say the FinFET 7 nanometer process is 0.7 volts. The fast corner will be simulated at 0.77 volts. And the slow corner will be 10% less, 0.63 volts. And again, temperature, the typical corner is actually at 70 degrees Celsius. So chips are actually expected to operate around 70 degrees Celsius because although the environmental temperature, the ambient temperature is like 30, 35 degrees, but because of the current that is actually going through the device, there's local heating. That local heating can raise the junction, the temperature of the MOSFETs and all that to pretty high, between like 70 degrees, and at the slow corner, that's at the high temperature, is about 125 degrees Celsius. So usually your IC is kind of rated to operate within a certain temperature range. Well, because as you change this temperature, you're operating the fast corner, the slow corner. Sometimes if you're not careful with the design is not robust enough, you will break the max delay constraint, you will break the mean delay constraint. That you might actually create race conditions in the fast corner. You might actually have situation where you violate hold time and setup time in the slow corner. That means the logic is too slow in propagating, you will violate those timing. So when you have timing violations and the process corner, it means that under these sort of process variations and things like that, you will see your design will fail. So normally you try to simulate in these process corners to see how robust, how strong is your design, how capable of design still to meet the specifications under these different process corners. And this table is quite nice. This is from the West and Harris textbook. It's actually showing you how there's some typical combination of process corners to look at different outcomes. So if you're actually looking for timing specification for bin parts, means you are actually trying to classify the parts, right? Just based on timing specifications, you set NMOS, PMOS, and wire to be typical, but you run that in the VDD and the temperature slow corner because this is the lowest VDD and temperature that your specification allow. And then if you want to be really conservative, like you want to really say that what is the worst case timing, I want to make sure I meet the worst case timing. If you're going for a really reliable chip, you will simulate this and make sure it passes the timing at the slow corner. But also you have to check the timing at the fast corner to see if you actually do not have race condition, which is the violation of mean time delay, and you meet the whole time constraints and things like that, and then you see what's the effect of noise. And if you are checking the effect of power, then you run the slow corners, but at the fast corner of VDD, this is to look at how, let's say this is on the higher end of dynamic power, and if you're looking at like leakage power, then this will be the situation. And there are sort of different sort of combinations if you want to go in more detail to see how your circuit would stand up on some corners, some operating corners. And this process corners, normally the NMOS and PMOS, you say it's like 5%. I think I'm not sure, is it 5 or 10% slower? But there is a typical number, and you would actually assume that there's variations would be that certain percentage slower in terms of the time, the delay of the time. Okay, so that's in general process corners. So again, this is showing you the range of NMOS and PMOS, just illustrating to you. But the key idea here is that you cannot just simulate and check the performance of your design at what we call the typical corner, right? You have to create a design that is a bit more robust, that can withstand variations in the operating environment, that is the VDD and the temperature, and also that can withstand to some degree variations in the fabrication environment, that is the NMOS, PMOS, and wire corners. So you have to simulate the design at these different corners just to see, well, will it pass and will it not pass, right? So you have to simulate the design at the design corners. And your Liberty file, the process development kit, also has the transistor models, the logic gate models, the standard cell models at these process corners. They have at the fast and slow, FF and SS corner, right? So if you check what we've covered in the past sessions, you will see, or also in the Google Silicon Initiative, the 130 nanometer process or the 180 nanometer Global Foundries process, you see you also have the process corner models, the FF, SS, and TT corners, right? So we're talking about process corners, and usually most of these chips, they will go through what we call a burn-in process. That is, after they are made, they'll actually be heated up to artificially fail those early fail. Because these devices, you make them, right? And then there's going to be a certain percentage that will fail early. and a certain percentage that will fail late. And they tend to have this sort of bathtub curve, reliability curve. And so what they call this process called burn-in is where they take the device that is manufactured and then they heat it up. And when they heat it up, it's like you're accelerating the decay time. So those devices that will fail early, will also fail because of this burning process, and then you discard them, right? Because it's very expensive for you to ship um, malfunctioning IC to customer. So better you identify them in the facility, throw them away before you send to customer. So these are just all some of the standard things that are going on. But what I wanted to actually focus on would be actually the 7.5, the statistical analysis today. So if you look at reliability, you're looking at oxide wear out, hot carriers, negative bias temperature instability, time-dependent dielectric breakdown. This is the last portion of the class on aging. So there's some equations here on aging, but I also provided some material. And you have aging of the transistors themselves through these mechanisms. And you have aging of the wires themselves, which is electromigration and self-heating, right? So both the wires and the devices, they will decay, they will degrade over time, right? But this is covered in the last part of the class, right? The last section on aging. Today, we're not focusing on aging. Today, we want to look more on the variabilities due to the process variation. So I'm going to skip all this part of scaling. Scaling actually is quite nice to read. It gives you a historical perspective because in the older days, about roughly 10 years ago and earlier than that, the next generation transistor, usually you have, you have a doubling of speed with the reduction and maybe a quadruple reduction of power and all that. So all those are great. That's called Moore scaling. But nowadays, that scaling law is a little bit broken already because we are so small. There's still improvement, but you hardly see too much improvement in speed. It's more of maybe density and maybe a little bit of power, but not too much. It's more of density improvement only. So the scaling part is no longer true because we are down to like 3 nanometer devices. So you're just getting density, but you're not getting the benefits of power reduction and speed increase anymore. But you'll still be able to squeeze more devices. So today we're actually focusing on statistical analysis of variability. Now, where are we going with this? We want to be able to sort of predict, okay, given certain variance of certain process parameters, let's say the doping variance or the line edge roughness variance, I want to be able to estimate how much worse or how compromised will the critical path delay be of my circuit. So we are going to characterize process variability by its effect on delay of my circuit, right? Because the key effect of process variability is you cannot assume that your circuit will operate at a certain performance. That performance actually will be much worse after looking at all the variability. It's not that the per chip, right? But if you're making like 10,000 chips or 1 million chips, right? Maybe 3 of them will be much better than specs, right? But on average, there will be a few of them that will be performing on this worst case, right? But you are selling all of them to the customer. You basically don't have the capability to test all of them. I mean, you can do a brief test, but you cannot test the speed and the performance of all of them. So what you do is you just have a specification that says all these chips, I guarantee, are going to perform above a certain frequency or at a certain speed, right? But how you choose, how you evaluate the speed is not, as I said, it's not the design speed because process variation makes that worse. And we're going to see how and why. So I'm going to assume that you already understand random variables. Of course, the two major distributions are uniform random variable and normal random variable. But if you at some point don't quite understand this, feel free to ask the question about random variables and all that. But I'm not going to cover random variables because I'm assuming this already covered in undergraduate. But if you can't follow at some point, please talk to me. So what happens is that there are a few sources of variation. Okay, so if you go down, so we're going to skip the math here first for a while because I will tell you about the sources of variation. Then we'll go back to the math on how, why you need to understand how random variables are combined and all that, right? But first, let's just talk about the sources of variations. Why is that process variation in the first place? So the first, of course, is the channel length variation. And there are several different kinds of variations. I should go to that first. See, where is that? There's several different kind of variations, 7.2.3. Lot to lot, wafer to wafer, die to die, and within die. Okay, so normally there's a wafer. Okay, there's a wafer that is the silicon ingot is actually sliced into wafer. So let me show you what a silicon ingot is. So silicon is a crystalline material, and it's actually this high purity material that is actually grown like this, right? So these are called ingots. Okay, so this is actually maybe the fabs will purchase these from some specialty companies and all that. And what happens is they're actually going to slice this into very, very thin wafers. So wafers like this, and these wafers, they are crystalline, and they have a very repetitive and very predictable structure. That's why they look like mirrors, right? And they're actually kept in very, very pure, clean environment, like no hands touching this. All is done by robotic handlers and all that, which are very clean. And even these wafers are actually in clean rooms where they actually measure the quantity of dust, like 100 ppm, 100 parts per million, and so on, right? Because you have one dust land on the silicon wafer, that's enough to short or to kill a bunch of transistors and things like that. So the fabrication has been done in a clean room, in very clean situation, and you start with this is silicon wafers. So you have all of this. So one lot is where you process a bunch of wafers together, right? Because the machine is set at certain operating parameters. You've got certain chemicals from certain batch, right? So that is one lot where I do all the processing for that time, right? The machine is having a certain settings. Why do you have lot to lot variation? Because sometimes when you turn on different day, you turn on the machine, you turn off the machine. Sometimes the heat will not quite be the same. Sometimes the chemical will not quite have the exact same purity and things like that. So they're actually very stereotype steps to be followed. So you might have what you call lot to lot variability. Wafer to wafer availability is, as you saw, um, you have individual wafers. So how is the chip made? There is a mask that is actually put on top of this, and then light is shown through the mask. And on the wafer, they actually put what we call photoresist. That is a chemical that when it's exposed to light, some of it will harden and some of it will not, right? So when it's exposed to light, there's certain regions that will be changed chemically and certain regions that are not. And then you will wash this with some kind of acid, and that acid will only be able to remove certain regions that have not been changed by the light, for instance. So that's the photolithography process. Okay. So you will do lithography on these, and within each wafer, there will be many, many different chips. So I see on silicon wafer. So the wafer can be big, right? So there's 8-inch, 12-inch, and 15-inch and things like that, right? So you see a lot of this repetitive pattern because these are all the transistors and their wires already fabricated or already done the photolithography. But you have many, many chips. Maybe in this wafer, you might have 1,000 chips and things like that. And what happens is this wafer will be diced. After the fabrication, they'll be cut. All these things will be cut, right? And then the edges one that are incomplete, they just throw them away. Okay. So you have variation between wafer to wafer. You make one wafer, you make another wafer. Again, the chips, even though it's the exact same design, exact same photoresist, exact same mask, there will be variation in the performance of one wafer to another. Because maybe again, a certain wafer you slice in the ingot. Sometimes when you slice, you will introduce certain stresses in the material, pressure or something like that, stresses on it, and then that change slightly the silicon properties, right, between the wafer. Or for some reason, this wafer is slightly misaligned, slightly tilted in the machine, right? Or you know, something like that. So there will be different sources of variation between wafer. And nowadays, within one wafer, let's say the chip on this side and the chip on this side, even though it's the exact same design, exact same situation, they may have different parameters. So this is wafer in wafer variation. And you see that because again, this wafer, as they get very big, they're not 100% flat, you know, there's actually a slight curvature, you know, and the chip quality of the chips on the side may not be as good as the one in the middle and things like that. And like I said, this wafer, you know, you look at it, it looks super flat, but on a microscopic scale, there may be bumps. You know, this thing is not exactly straight and things like that, right? Because, you know, it's a bit heavier in the middle and all that. So all these effects all come into play and they give you lot to lot, wafer to wafer, die to dry or within wafer. And again, within die. Within die means in one chip itself. Even in one chip itself, let's say you're looking at one chip itself, like one chip here like that. There's a variation of the transistor that you make at this corner versus this corner. And we are at that level today where intra-die, within the same die, within the same chip, you cannot actually make the same transistor in the same chip because of again different things lah. Like when you make the transistor nowadays, okay, photolithography is a process where you are shining light. You're using light to actually create patterns on the photoresist so that you can cut away these patterns, and you're playing some fancy optical tricks. In those old days when you are at 180 and 200 microns, 200 nanometers, and it was still maybe a bit appreciable because the wavelength of light being used to create these patterns is on the order of 157 nanometers. 180 to 157. So it's in the deep ultraviolet light wavelength. So when I talk about 157 or 183 nanometers of light, this is roughly like half the size of the maximum, the minimum, the smallest dimension that you can etch with light. So nowadays you see, okay, I have 157, that's the wavelength of my light. But how am I able to actually create features on the size of 3 nanometer when my light is only on the size of 100 something nanometers, right? That's because they play a lot of fancy tricks using interference patterns with the light. So this is called diffraction patterns. They have some fancy patterns where they are able to mathematically create smaller patterns due to certain tricks they play with the light. And they also do this lithography immersed in high index material. So they don't do it in air, they now immerse it in some kind of oil or some kind of liquid so that you can get higher resolution. And they do fancy tricks with Fourier transform on this light to get those features. So there's a lot of very fancy tricks to do that. And why am I saying that is because when you use this Fourier transform, you know from Fourier transform, sharp edges is not very well defined. So if you want to, what happens is maybe somewhere in the middle is okay, but towards the edges, it gets a bit fuzzy. It's not very sharp when you create this type of edges on devices. So you can expect the quality of the lines or the features or the geometries that you're trying to build on the IC at the edge is not as consistent as somewhere in the middle. And this is why nowadays when you make, let's say, repetitive devices, like you make RAM and all that, typically what happens is people will draw a few extra rows and columns of the device, but they will not actually use them. They'll just draw them, include them in the chip. So the same, let's say you have a row of adders, right? If you want to have that adder to be very consistent, you have a few other rows of adders to the left and the right. The additional adders are actually not functional. They are just created to create a very stereotyped environment around your transistors, around your logic gate, so that you can control the process variability. So you are actually using real estate. You're actually using additional chip area to control the process variability. You're creating redundant structures, redundant logic that probably is not used, all for the sake of the part where the logic is used, the space where the logic is used, so to make that more reliable. And the main message, as I'm mentioning here today to you, is the within die or intra-die variability is quite significant nowadays lah. So if the intra-die is already significant, no need to talk about die to die, within inter-die, within wafer, wafer to wafer, lot to lot, all are also very significant. Okay, even on one chip itself is so significant, the variation, the others are so significant because we are already in the domain. Things are so fast that from one end of the chip to the other end, the transistor can look quite different lah. And not just that, but the delay for you to actually send the signals will be quite different. So there are various kinds of variation. So here, for example, is showing, this is from 2006 itself, already showing the frequency. What they do is they build ring oscillator. So a ring oscillator is a very simple circuit. It's basically a bunch of NOT gates, odd number of NOT gates that are connected in a feedback fashion. So what happens is, you can count the propagation delay of all these NOT gates. That is half the period of the clock. So a ring oscillator is just basically creating a digital clock, right? So the signal here is going to take 3 logic gate delays before it will change, right? So then another 3 logic gates. So the clock here that's going to generate it will have a period of 6 logic gate delays, 6 inverter delays. So you can control the frequency of the ring oscillator by controlling the number of inverters that you connect, but it has to always be odd number. Even number, you will not get an oscillator. You'll just be steady like that. Okay, and again, a lot of people make this mistake from Keeler. So what they did is they want to test what is the within wafer. So this is one wafer. So they create ring oscillators over all the wafers, exact same ring oscillator, and then they are actually looking at what is the frequency of the ring oscillator, and you see it varies by plus minus 15% thereabouts. So from less than 80 megahertz all the way to 110, 120 megahertz. It's the same wafer, right? It's the same process, same wafer, everything, but just putting it at different parts, fabricating it at different parts of the wafer, you get different frequency. Exact same design, exact same standard cell. So this is just showing the severity of it. But this is already, this is within wafer. Now we're talking about within die, within the same chip itself. There is variation. Okay, so now we talk about this variation. Where does this variation come from? What causes this variation? Well, this variation comes from a few main ones. Number one, you're trying to draw a device with channel length. Right? So this channel length will have 2 types of variation, within die variation. If this is a correlated variation, means everything sort of changes the same. This is called across chip line width variation, ACLV. Or if it's random, it's called line edge roughness. So basically, what this is basically you're trying to draw a channel. The channel is maybe 7 nanometer or 180 nanometer, but when you fabricate this within the same die or within the same chip, not all your transistors will have exactly 180 nanometer. There's going to be some roughness, right? Some will be 185 nanometers, 190 nanometers, because it's not really a straight line. There's going to be some jagged edges at that, right? So this line edge roughness that can be correlated or random variations, right? Because of the patterning. So again, the channel length is varying because of your inability to control precisely the channel, the drawing the channel. And this is one main source of variability. This one main source of process variability in that causes like intra-die variability. Okay. The second is the variability that leads to changes in the threshold voltage of the transistors. Okay, and this is actually caused by random dopant fluctuations. That is, I want to dope, maybe I want to dope additional 10 to the minus 10 to the 5 per meter square or something like that, right? And within that transistor, sometimes I have a few more dopant atoms, sometimes I have few less dopant atoms. And this is called random dopant fluctuations because they are modeled as random addition or subtraction of dopant atoms. And when you change the doping profile, of course, you're going to change the threshold voltage. Threshold voltage, remember, is the minimum voltage you have to apply on the gate in order to create a conducting channel to connect source to drain. And what they do is that they try to estimate how the threshold voltage, they try to capture this parameter in terms of a statistical property, the standard deviation. So the line edge roughness will lead to certain standard deviation, and the threshold voltage variation will also be lead to some standard deviation. And the threshold voltage variation is dependent on the length and the width of the device. So if your transistor or your standard cell has a smaller length and a smaller width, the variability, the standard deviation of that threshold voltage is going to change more. It's going to be more variable. And the third major effect of process variation is the oxide thickness. How thick is your oxide connecting your gate and your bulk? Right? There's some variability there, but it does affect things. Okay, so there are three sort of main sources of process variation: the channel length variation, the random dopant fluctuations that lead to threshold voltage variation, and there's oxide thickness variation, which also will change the threshold voltage. Okay, and I've given you a paper by Saha. This is an old paper, 2010, about 13 years ago now, but it's a good one. He actually explains in more depth. It shows you all the modern transistors, and it talks about random discrete dopant. This is RDF, random dopant fluctuation, same thing. Okay, and then it talks about line edge roughness, and then sum of effects, and it talks about the dielectric variability. So it shows all the random dopant fluctuation, which leads to threshold voltage variation, line edge roughness, and oxide thickness variation. Then there are a few others that they talk about. And they try to give you a comparison. How does the standard deviation of line edge roughness compare with standard deviation of threshold voltage due to RDD? So all of these, line edge roughness, random dopant distribution, and oxide thickness, their variability changes the threshold voltage. All three of them, their variability changes the threshold voltage. Right? They said the standard deviation of threshold voltage from the line edge roughness, the standard deviation of threshold voltage from random discrete dopant or random dopant fluctuation. So all of them will change the threshold voltage. If the effects are independent, they're not correlated, the total standard deviation of the threshold voltage is basically estimated by the root mean square of the two independent sources. So I have tracks like oxide thickness variation of the threshold voltage. I have random dopant fluctuation variation of the threshold voltage, and at some point I also will have line edge roughness variation of the threshold voltage. If I can estimate the variation due to oxide thickness, due to random dopant fluctuation, and due to line edge roughness, I can estimate the total standard deviation of the threshold voltage variation due to each of these individual physical effects. Okay, this is where we start getting into the statistic, because you will actually be playing around these numbers to actually estimate all of this, right? And the key point I want to actually disentangle this to you, because there are many details, don't want you to get confused. Process variation, there are several physical effects that give rise to this. West book covers three: oxide thickness, random dopant fluctuation, and line edge roughness. Okay, three of them give rise to variations in threshold voltage. Okay, they contribute to a standard deviation in the threshold voltage within the same die. Okay, but when we are trying to estimate the effect of all of this process variation, we are going to be totally in terms of how variable is the threshold voltage? How much has the threshold voltage changed, right? And that threshold voltage change will come from a variety of effects. Like I said, it's going to be from line edge roughness, from random Dopant fluctuations, from oxide thickness, and Sahab's paper also gives you several other sources, but other than these three, TOX, RDD, and LER, they don't actually show how to estimate the variability from these others, like the high K dielectric or polysilicon granularity. But if you like, you can actually look it up. But we're only focusing on these three main ones because these three main ones seems to be the dominant one at the moment. Okay. Right. Now, how do we relate this variation in threshold voltage to speed variation in the performance of my circuit? So when I talk performance for circuit, normally I'm only interested in three main things. I'm interested in speed, I'm interested with energy consumption. That's covered in OAE 5163, low power VLSI. We're not covering in this course. And I'm interested in area, right? So I have a I can say I have a high performance VLSI circuit if my circuit runs very fast, it consumes little energy, that's what I want, and it uses a small area. Normally these three are like sort of mutually exclusive. Okay, so you can trade off one for another, right? So I want to know, because now I'm starting to show you that there are ways that you can estimate the variation in threshold voltage, right? You talk about it as the mean and the standard deviation, right? And you can apply either a uniform distribution or a normal distribution. Normal distribution is more natural, because from this law of large numbers. So you normally what you hope for is your threshold voltage. It will be the design parameter will be the mean value. So if you want your threshold voltage to be, let's say, 0.2 volts, for instance, you design your transistor to be 0.2 volts. So your hope is the mean will be 0.2 volts. But there will be a standard deviation, a variance of threshold voltage that you will be able to fabricate, right? Because although you design for the mean, but the process variations could be due to random dopant fluctuations, could be due to line edge roughness, could be due to oxide thickness variability, will lead there to be a variation, a spread, right? You don't achieve one threshold voltage, you achieve a statistical distribution of threshold voltage. I mean, of course, statistical distribution is just the way we think about it. I mean, every single transistor will have its own threshold voltage. You can actually go ahead and each of them has the threshold voltage doesn't change in each transistor. They're fixed, but if you want to think about the effect on the circuit, it's easier for us to model it as a statistical distribution, that this circuit has a variation of threshold voltages, and the threshold voltage will be about a mean with a certain standard deviation or certain variance. Okay, so the standard deviation can be estimated, right, from all these parameters. These are all circuit device parameters, and it's a function of the length and the width of the device. So if you have a larger standard cell, like say X times 2 or times 4, the threshold voltage of that particular standard cell the variation will not be as large as the unit size or the smaller size one. And think, yeah, so this is also this is a coefficient, right? They depend on the doping level, the energy level, the Fermi level, and all that kind of stuff from semiconductor physics. But it can be estimated, right? And this can be given to you, or you can estimate from device parameter. So this is due to the random dopant fluctuation. Line edge roughness also, I think there is sometimes they can estimate the standard deviation of that. How does that line edge roughness lead to a certain variation, standard deviation in threshold voltage, or certain deviation in speed, and so the oxide thickness is the same. Okay, so now what we're trying to do is we're trying to see how to how to apply that threshold voltage variation to speed. What is the relationship? To check the relationship, we look at these two equations. This is the equation of your the current voltage relationship for your MOSFET. PMOS, NMOS, but it's missing the mu Cox. There's a parameter here, there's a constant or proportionality here. That's why they use proportional, they don't use equal. And so this is the off current. The off current comes from bipolar junction transistor, the diode equation. Here, this from the equation, and the on current is coming from MOS. And because this is a short channel device, it's not long channel, so alpha is no longer 2, it's not a square device. Alpha is closer to 1 point something because of short channel effects like velocity saturation and all that. You do a sensitivity analysis. That means you look at how ion changes as a function of changes in length, and how ion changes as a function of changes in threshold voltage. Because it's dependent on both on length and threshold voltage, you get this equation. Ion nominal is the standard ion. You see that the change in the drive current is going to be a function of the variation in L over the actual length. That means if I'm looking at 180 nanometer devices, and my device has a change of 2 nanometers, so the change in current is going to be 2 nanometers over 180 nanometers. That's the percentage change of the current due to that change or that variation in the length. Similarly, the change in the threshold voltage, okay, is going to be a function of alpha over VDD minus V threshold, right? So how big or what is the effect of any change in threshold voltage or any change in channel length on the current? You can look at this effect, the magnitude. So you can now say that you then can now sort of estimate a 10% change in channel length or a 20% change in threshold voltage. What would be the percentage change on the drive current of the transistor? Okay. And from this, you can do a direct proportionality, because current, transistor current, drive current is directly proportional to transistor speed. You increase the transistor current, you speed up the transistor. You reduce the transistor current, you slow down the transistor, right? So once you got the percent variation in terms of transistor current, that is equivalent to the percent variation in the speed of the device. So now we've connected all the dots together. We've been able to link changes in channel length and changes in threshold voltage to changes in current, and the changes in current is equivalent or directly proportional to change in speed. I'll give you an example. So if we look at, let's say the channel length is changed by 10%. So 10%, you can think about it, the standard deviation is 10% roughly, you would say. Standard deviation of 10% with a Gaussian distribution means about 67% of the transistors will have this amount of offset within this range, up to this amount, right? So let's say 10% variation, how much would the current actually change with a 10% due to a 10% change in DL? So here, for example, this the 10% change in channel length causes a 10% change in current, right? Because this part here, 1 minus 10%, you change the channel length by 10%, you also change the current by 10%. But here's where it gets tricky. If you look at changing the threshold voltage, let's say if you change the threshold voltage by 10 millivolts, right? 10 millivolts of threshold voltage, and you have this sort of values. A 10 millivolt change in threshold voltage here will cause a 1.8% change in the on current, right? So again, you can actually estimate what is the impact of a certain deviation of threshold voltage on the current and the impact of a certain deviation of channel length on the current. And then that deviation current, so let's say 1.8% change in current also leads to 1.8% change in delay, in speed. Okay, I'm going to stop here for a while just to check, do you follow these ideas, right? First, what is the key idea? We're talking about process variation. And process variation, we talk about some main effects is actually arising from the fabrication of transistors. We're focusing specifically on intra-die, within the die effects. We see that some of the main effects can come off. You can actually have variation in the channel length, which will change, of course, the current, or you can actually have variation that will cause changes in the threshold voltage due to either random dopant fluctuation or random discrete doping, due to line edge roughness, or due to changes in the oxide, variation in the oxide. And all these three can be characterized as a mean and a standard deviation. And we see how to relate the mean and standard deviation of any change in channel length and any change in threshold voltage to a mean and standard deviation of current. And this mean and standard deviation of current is directly proportional to become a mean and standard deviation of delay. So I'm going to stop for a while, check, do you understand this concept? Any questions about this? Any doubts? So if you follow and you'd like me to move on, just give me a thumbs up. If not, feel free to unmute yourself or to type a question in the chat box. Okay, Felix has got the thumbs up. Maybe I just hold on for another 2 or 3 people. Okay, thanks Om Prakash, thanks Asri, thanks Rasman, thanks Umar. Okay, great. So you all understand the key equations. You all understand how to calculate all this. Now let's look at an example. Let's look at an example. Okay. Okay, a path contains 16 two-input gates, each with has a nominal 20 picosecond delay. Okay, now let's just draw this path. Let's see what this looks like. Okay, two input gates. Okay, so it says this path has 16 two-input gates. So we know that there are actually two types of two-input gates, the NOT gate and the NAND gate. Okay, so you draw this is one box. So now we have 16 of these boxes. 16. And they are sort of connected. This is like that. This is like that. This is like that. They're all connected. There's 16 of these. This is a path, right? It could be 8, there could be 32. This could be the NAND gate driving and maybe a NOR gate, driving another NOR gate, driving another NAND gate. This is what it means, lah. Their path has 16 two-input gates. And roughly speaking, they're saying that this has nominal delay. For simplicity, they say the delay is 20 picosecond, 20 picosecond, 20 picosecond, 20 picosecond, roughly speaking. That's what they say. Okay. But in reality, I want you to understand this is not 20 picoseconds. Right? This basically, if you make 1 million chips with this particular gate in all the million chips is going to follow a normal distribution with a mean of 20 picoseconds and some kind of variance, some kind of standard deviation. This is one standard deviation here, right? So this encompasses 67%. Okay, and this is also going to be logic gate. Out of the 1 million chips, if you look at every single chip and you do a histogram of every single chip, you're going to get here 20 picosecond, and then there's a sort of a distribution that arises from process variation. And you also know from the last session, this 20 picosecond is not a fixed amount. Let's say the up transition here leading to down might be 20 picosecond. The down transition here leading to up might be 15 picosecond. And then if this is the transition and this is high and then leading to up, it might be 10 picosecond, right? The delay of the gate will be varying, right? So I want you to be able to generalize all of these, right? That delay will still all be subject to some kind of statistical distribution due to process variation. And again, it does not mean that the delay is changing in one chip. In one chip, the delay is going to be that, it's fixed. It's just that when you look at 1 million chips, 2 million chips, and you check that particular logic gate in those 1 million chips, you do a histogram, you will see that the delay from in the different chips will follow a distribution, a Gaussian distribution. 20 picosecond is the mean with some standard deviation. And this variation arises from process variation, changes in channel length between each chip I fabricated, changes in the oxide thickness, how thick is this, and random dopant fluctuations, like the device I have more or less dopants. Okay, let's look at the question a little bit more. Suppose ACLV due to neighboring pattern density constant operators experience the same channel length variation, standard deviation of 2% nominal. Suppose RDF causes a 25 millivolt standard deviation in each transistor's threshold. Estimate the standard deviation in the path delay. So you see, at the end of the day, they want you to be able to estimate what is the standard deviation of this path. Okay, and they give you two situations. They said there is a correlated deviation, 2%, correlated channel length deviation of 2%, and that there is a random dopant fluctuation deviation of 25 millivolt. So what this problem is telling you is that I have, okay, standard deviation, so not this is 2%, and I have VTH, this is 25 millivolt. Okay, this is what this is telling you. Okay, so first step is they ask you to estimate this path delay. Okay, this path delay. I have 16 logic gates. So 16 times 20 picosecond. So my path delay is supposed to be 320 picoseconds. This is the mean of my path. Right? Path delay is basically the delay of this input change at this output, some change at this input propagating to change at this output. So you can just simply add up all the mean values. You get, this is the path delay, 320 picosecond. But what they want to know is they want to characterize process variation. How does these two process variation be used to estimate the variance here? Okay, and this is an important concept because if you know that you create a variance here and you say that I want to have a 99% yield, you will pick 3 standard deviation from this, the delay 3 standard deviation. This will be the delay that you claim that for your specs, right? So if the standard deviation happens to be 5 picosecond, you will take 3 of that, so 15. So 335, this will be 335 picosecond. You won't choose 320 picosecond. You say, I would select my specs to be 335 picosecond because with 335 picoseconds, 99% or 3 sigma, 99% of my devices will cover this, so my yield will be 99%. Right? But if you're happy with maybe 95%, then you go for 2 sigma, things like that. Or 6 sigma, I will actually have to go for 6 times. So the reason we're doing all of this estimation is because you can estimate the effect of process variation on the spread of delay, and you can use this statistical modeling to actually say what would be a realistic parameter for me to choose in order to achieve a certain yield. I want to meet a certain yield. Conversely, if you find that this is quite large, you can actually go and change your process to improve this, or you have to find a way to maybe reduce the variations in all of these, maybe make them correlated or something like that, right? But that's the key idea, right? This is why we're going through all this trouble, is for you to really be able to relate yield with the process variation. Okay. So let's now look at this threshold voltage change first, right? Because it's a little bit easier to see. A 10 millivolt change in VTH causes 1.6 change. Okay, they're using the same parameters as earlier, alpha equals 1.3, S equals 100 millivolt per decade, so N equals 1.6, and so they're let me just array this properly. So what we want to know is this dVt over nVt. This is the percentage change in ion. Okay, from here, the percentage change in ion. And this is actually alpha over VDD minus VTH dVTH. So VT in this particular design, alpha is 1.3, VDD is 1 volt, and VTH is 0.3. And then there is a 25 millivolt change, variation, right? The standard deviation is 25 millivolt. Right? We were talking about standard deviation of 25 millivolt here. So from here, you can do this calculation and you will find it will be 4.6%. It will be 0.046, 4.6%. So this means that this variation in a 25 millivolt variation in VTH, the standard deviation of 25 millivolt, will lead to a 4.6% variation of 320 picosecond. So 320 picosecond times 0.046. This will be, let's just take the shortcut and look from the book. Sorry, I'm just going to take my calculator and calculate this out. 4.6%. Zero 0.46 times 320 is 14.72 picoseconds. So it's going to lead to a variation of 14.72 picoseconds. Now, if VTH is the only variation, that means you can model the delay of this path as okay. Sorry, not this path. Let me talk about single gate first, right? Because this 25 millivolt across the board, right? So if we are talking about a single logic gate, right now you can tell The mean is 20 picoseconds. And if we are looking at 25 millivolt standard deviation of VTH, it's going to be 20 picoseconds times 0.046, which will be 0.046 times will be 0.92 picoseconds. So this one standard deviation, this will be 20.92 picosecond, and this one will be 19.08 picoseconds. This is your model for one gate due to a standard deviation of 25 millivolts. It gets a bit tricky when you want to add it all up, and that's where we are for the path, and that's where we are looking at. That's why I paused this now, because there's additional step here. There is only 4.6 or squared by 24, because the standard deviation. Okay. I will have to now go back to the statistical laws. Okay, they talk about that. Okay. We have now seen how to model one single gate, and I'm just looking at the threshold voltage standard deviation. And now what we're trying to do is we're trying to see what is the effect on the entire path. And that is requiring us to add random variables between gates. And because the deviation of this VTH, because it's due to random dopant fluctuation, it's not really correlated between the two. So they're independent random variables. So we have to study what happens when you start adding random variables together. Okay. When you add random variables together, okay, so in this case, what we're doing is we want to add this distribution to another, for distribution of this gate, to the distribution of this gate, to the distribution of this gate, to the distribution of this gate, and so on, right? So you want to add random variables together. When you add random variables together, you will add the mean and the variance is actually reduced by a factor of n, the number of random variables. So the mean is the sum of random variables. So this is the mean of the path, and this variance of the path is actually the variance of individual random variables divided by n path. That's why the standard deviation of the path is actually the standard deviation divided by square root over n. So if I add more of this, my mean will go up because it's just add, but by my variation will go down. Right? It's somewhere here. I just can't find it. I just can't find the text that says that. But this is the this is like standard statistics. The standard deviation will go down, will scale down as a square root of n, the number of the sums, right? It's coming from summing of random variables. Okay, so how do they actually get 24 here? But that's the challenge. How did they actually get 24? Okay, let's look at how that goes. 16 plus 8. Okay. The thing is, they're doing some sort of estimates lah, because it goes back to the logic gates lah. Okay. If you have a, so this will be, if this is 0, 0, then this will be 1. This is a NAND gate. And you also have a NOR gate. Okay. If I connect these two gates together like this, okay, I'm probably going through 2 transistors here, and I might, depending on the gate, I might be going through 2 transistors here, or I might be going through 1 transistor here. So what I'm saying is that when you connect up many of these gates, okay, you have many possible logic, right? You may actually be logic 1, going to logic 1. So you go through 2 transistors, 1 transistor, 2 transistors here, or 1 transistor. So it's possible for you to actually pass through 2 transistors or 1 transistor, okay? So if you have 16 pass, the most number of transistors you pass through is 16 times 2, 2 transistors. And the least number of transistors you pass through is 16. But you're not quite sure how many transistors you pass through. So what they do is they assume on average you go through half of it, you go through 2 gates, half of it you go through 8. So it's 16 times 1.5. So this is 24. Okay. And why this 24 magic number comes from is because these variation in VTH, this is for single transistor, right? Because remember we were looking at the equation of the sensitivity equation of for current. The current equation here. This is the current for 1 transistor. It's not the current for 1 logic gate. It's the current for 1 transistor. So when we are checking the effect of cascaded gates, we have to count how many independent transistors that we are passing through. So here they do a shortcut. They just do some approximation. They say, roughly, I assume I will on average pass through roughly half 2 transistors per gate, and the other half is 1 transistor per gate. So that's why you get 24. And that is why when you are considering the variance due to a path, okay, they estimate it by taking the 4.6% divided by square root of 24. That is 0.95% is the standard deviation of the entire path. Okay, so this is where the 0.95% comes from. This is where the square root of 24% comes from, because you are now combining the individual random variables, and now the random variable is actually a measurement of time delay, right? Because remember, we were able to estimate the time delay distribution, the mean and the standard deviation due to VTH change for one transistor. Then we are looking at the whole path now. So we have to do this funny thing about how we combine the means and how we combine the variances and to get standard deviation, and we count how many transistors. So now we are able to see that the standard deviation of the entire path due to VTH is 0.95%, 0.95% of 320 picosecond. Okay. It doesn't end here. This 0.95% standard deviation is only due to VTH. Right? This is the standard deviation of time due to VTH. We also have the standard deviation of time due to channel length changes in L. That's from ACLV. And it's 2%. It's going to be 2%. Right? 2% here, as you can see. The low one cursor is missing already. Okay, it's going to be 2% here, right? Due to the channel length variation is going to be 2%. So we see that 2% change in length leads to 2% change in current. 2% change in length leads to 2% change in current. So the standard deviation for one transistor due to channel length variation is going to be 2%. And because this is correlated, the standard deviation for the whole path is also 2%. We will look at the uncorrelated case. Uncorrelated case will be different. So it's going to be 2% here. So 2% of 320 picosecond, we will find is 6.4 picosecond, and 0.95 picosecond, 0.95% of 320 picoseconds, roughly about maybe 3 picosecond. So then you now have to combine these two together because they are independent effects. The total standard deviation of the time is actually 6.4 picoseconds squared plus 3 picoseconds squared, the whole thing square root. So it's roughly about maybe 7 point something picosecond. So now you can model for this entire path, the distribution is 320 picosecond. 1 sigma is 327 picosecond. Okay, I'm going to stop here to check if you can follow this argument. So where it got complicated, I think it's probably straightforward for you to get up to the point, how do I get the time distribution? That means the delay distribution, the mean and the standard deviation for one transistor. But it starts to get complicated when I am actually combining it for a chain of logic. I have to count the number of transistors it passes. And then I have to evaluate the effect of two different sources of time variation, of delay variation. That's where it gets complicated. Okay, so I'm just going to pause a bit. If you follow this, if you follow it, give me a thumbs up. If not, please ask a question, because this is where most of the tricky part comes from. It's just how do you combine all of these? You have to look at the circuit, and then you have to be able to basically combine it now. Yeah, with the different statistical rules. Okay, good. Lukman and Felix are okay. All right. If there are no questions, I'm just going to go on. Let's look at the correlated versus uncorrelated effect. Okay, so ACLV, across chip line width variation, is a correlated channel length variation. Line edge roughness is random or uncorrelated effect. There is a rule here, you have to divide by something if it's uncorrelated. Random variables. Yes. If the variations are independent, the variance reduced by a factor of n by m. The number of stages, that means the number of logic, and the number of transistors. Okay. So Because it's correlated ACLV, this is 2%. But if it's uncorrelated, this 2% will have to be divided by square root of 24 as well. Okay, so you have to know whether it's correlated or uncorrelated. And again, Saha here also talks about correlated versus uncorrelated. Doesn't talk about it. Okay, anyways. So I think the main complexity is for you to first be able to convert from threshold voltage variation or channel length variation, certain amount of that. How do I express it in terms of the variation in delay for a single transistor? Then the second difficulty you have to work on to really understand and be able to do is if I give you a delay variation, threshold voltage variation, or line edge, let's say a standard deviation of the delay for a single transistor, how do I estimate that for the whole logic path? And then the third difficulty is I have multiple sources of that variance or that standard deviation. How do I combine that for a whole logic path? So walking through all of these like that, but you know, in the exam, I can give you something like this, right? I can actually say, okay, this is the circuit for maybe a full adder, right? Or a comparator, right? So I can have maybe my majority gate here for full adder kind of thing like that, right? Then I ask you to, and then I would say, for example, like if you a process variation, I can say maybe VTH is, maybe I give you certain 5 millivolts or something like that. And then the variation in channel length is maybe 5% or something like that. And then I'll ask you to estimate what is the timing variation, or I can give you a circuit and I just give you values and then ask you what is the impact on the circuit. Then you have to basically identify the critical path first, right? Because here they give you this path. This path is interesting because this is the critical path, right? So likewise here will be, you actually apply the analysis on the critical path. You should be able to convert for each transistor in that particular logic gate. What is the effect of this standard deviation on the standard deviation of time, the delay, this effect on standard deviation on time, you'll be able to draw that model. And then how do I combine and all them to estimate the effect of the entire path? And then how do I combine the effects of these two independent sources of variation to impact the whole thing? Okay. Now, there's one last challenge to actually tie this all up together. And that is what happens when you have multiple paths, maximum of random variables. Early on, what we're doing is we're talking about adding random variables. So I got this, the timing of the transistor here is one random variable, plus the timing of the transistor here, another random variable, plus, and you know, I could have two or more transistors here. So it could be two or more of those transistors added together, plus these transistors, plus all the other gates. That's addition of random variables. We have another issue, which is that if we have a bunch of paths, right? So now we have the issue that now we have the situation where you should be able to estimate this particular logic path. What is the distribution? What is the mean? And then what is the standard deviation? And now I tell you that there are a bunch of these logic paths. Okay, so I have a bunch of this distribution. This logic path number 2, logic path number 3, logic path number 4, right? And they are roughly same mean value. If I have a circuit that has all of these, what is the maximum delay? Maximum of random variables, right? Because if I have a circuit of all of these, right? Let's say my circuit consists of 4 logic paths with this type of 4 of this distribution. How should I pick the maximum time? How should I pick the max delay for my circuit, right? Because if it's just one path, I can actually say, okay, I pick, if I want to have a 99% yield or 95% yield, I pick 95% yield will be 2 standard deviation. I pick this, right? Then I have 95%. But the problem is I have 4 of these sort of critical path or near critical path. That means their mean values are almost the same. Standard deviation, something similar. How do I pick, right? Do I pick the largest? No, that's not what you do. What we do is we look at a result here on the maximum of random variables, right? And we observe something interesting. If you have one random variable, okay, this is the mean and this is the standard deviation. If you have 2 random variables with the same mean and standard deviation, the mean is going to be slightly increased. It's not going to be 0.5, it's going to be 0.56, and the standard deviation is going to be increased, right? So what we observe is as you add a lot of path, right? As you talk about 10 distributions with the same mean and variance, the maximum path has its own distribution. So what I'm trying to say is that now we are doing a statistics where we are looking at these 4 paths and we are coming up with a new statistical distribution for the longest path combined, taking into account all these 4 paths. That's what we're doing. Okay, so we can use these statistics here, these results here. They're saying that if they have one and n path lah, n path, 1 path, 10 path, 100 path, 1,000 paths with the same mean and same standard deviation. If we combine all of that, what would be the new distribution representing all these paths? So the new distribution representing all 10 paths will have this mean and this standard deviation. If the new distribution representing all 100 paths will have this mean and this standard deviation. The new distribution representing all 1,000 paths will have this mean and this standard deviation. What you notice is that as you have more paths with roughly the same mean and standard deviation, you look at all these paths together, the delay seems to be increasing the mean, whereas the variance is reducing. Okay. And this is where we actually start to worry about. We say that the critical path alone is not enough. If we have a lot of path that is near the critical path, right? By this sort of estimate, we will know that just looking at the critical path is not enough, right? We will have a new sort of statistic or new distribution taking into account all these near critical path, which will lead to longer delay, right? So that's what this part here finally is looking at, is that now that you can estimate the distribution for one path, okay, I can ask you to say, okay, now tell me for this particular circuit, I have maybe 100 of this path or 1,000 of this path, right? Tell me what should be my clock frequency if I want to have a 95% yield. So you cannot use this same distribution. You have to actually come up with a new distribution, which is this maximum of normal variables distribution. You look at how many how many paths that are near critical. Then you look at what will be the new mean and the new standard deviation. And from this new distribution, this is the distribution that represents all the paths, right? All 10 paths or all 100 paths. And you only consider the near critical path because these are the dominant paths, right? They are quite similar. So you should be able to now look at a chip which has a bunch of near critical paths and estimate and come up with a new distribution representing the critical path of that circuit. And again, I want to remind you, why is there a variation? Why is there a variance and standard deviation in this path, right? It comes from process variation at the single gate, single transistor level, which we then has been able to cascade into path and then multiple path at the end of the day. So I'll give you an example, like for instance, if this chain, right, which we already modeled, we've already modeled it to be we've already modeled this chain to be logic chain to be 320 picosecond mean with maybe a 7.7 picosecond standard deviation, right? And somehow this logic chain is replicated in, let's say, NVIDIA GPU. There are 1,000 adder unit. This is within one of those computation units. So there are 1,000 of that. So I know I will have 1,000 of these paths already. So I can come up with a new statistical distribution for those 1,000 paths, right? Mean is 3.24, standard deviation 0.35. So I can come up with a new distribution 3.24, standard deviation is 0.35. I can come up with a new distribution where this critical path is present in 1,000 compute elements. So for that whole chip, I can come up with a new mean 3.24 times 320 picosecond. So the new distribution will be 320 times 3.24 or 1,037 picoseconds. My new distribution will be 1,037 picosecond, and then 0.35 or 77 is roughly divided by 3 lah. So it will be something like this lah. The standard deviation will roughly be something on the order of 2 picoseconds, right? So if I'm representing, let's say an NVIDIA chip GPU with 1,000 of these near critical paths, I can represent the distribution of the near critical path due to process variation as having a mean of 1,037 picoseconds with a 2 picosecond standard deviation. And from here, I can say, oh, if I want a yield of 95%, I will basically take 2 standard deviations, 4 picosecond. I will say that my max delay will be 1041 picoseconds. And you can see this number is really far from 320 picoseconds plus 2 standard deviation, right? So this is why I'm emphasizing that process variability is really a challenge. And this is the case, especially when you have chips where you don't have one very, very dominant critical path, that you have many, many paths that are about the same delay. As you can see, in this case, I'm just looking at the chip where I have replicated compute units. Each of them have roughly the same delay, 1,000 of those replicated units like a modern GPU. And all of a sudden, your max delay is almost more than 3 times the critical path of a single chain. And this is only due to process variation. Right, so I'm going to pause here. We've covered 4 main concepts. I've just reviewed the 4 main concepts of how to estimate the effect of process variation on delay. Okay, first, you are going to be given some measure of variance, either on the threshold voltage or variance on the length. You have to be able to convert it into variance of the current, which then is equivalent to variance on the time. Okay. So you must be able to interchange this in terms of picoseconds lah. Okay. Second, this variance applies to one transistor. So you must be able to apply it to a logic path. Right, so that will be, you look at whether it's correlated or uncorrelated. If uncorrelated, the variance is divided by number of stages in the logic path times number of transistors per stage. Okay, if it's correlated, it's just that. Third, you got the delay. So you got the delay. So this is now the variance of the logic path. This is the variance of one transistor. Now you got the delay of the logic path. So you must be able to combine this delay from, let's say, RDD, this delay for the logic path. This is logic path from RDD, from line edge roughness, from oxide thickness. Typically, if they are uncorrelated, it's basically just this lah. And fourthly, you have now got the delay or logic path. Now you have to look at what happens with multiple near critical path. 4 steps. And this will put you into a very realistic situation, what we face in modern chips today. Right? So this is the main point I wanted to cover today, just to go through this. There are some, not too many, but few additional examples here. Like here, they're talking about the variations, and then they're actually asking you to estimate yield. They are connecting yield with variation. But as I say, once you actually can put this as a statistical distribution, you can calculate yield already. So there's some of this here. But this is the key point here. We've now gone through how to estimate the effect of process variations, statistically compute the effect of process variations. How does it impact the critical or near critical path delay? And as I mentioned, the main point is you are setting things like your maximum frequency that you can operate this, and you're also looking at what would be the range of delays or the range of performance that you can expect from your chip. That's what we're looking at now. Okay, so I'm going to pause here now to check if there's any questions. If there's questions, I'm happy to answer them, to repeat any part of the sharing. If there's not, it's okay. You can also always reach me by WhatsApp, but this is pretty much what I want to cover today. So maybe I'll just wait for another couple of minutes to see if you have questions on any of these. Like I said, what usually will happen is I will give you a different circuit and just ask you analyze the effect of process variation. So you have to go through all these steps. And again, your problem-based assignment is also doing this. You actually have to identify how many critical path, near critical path, microprocessor, and you just take it through all of these. No? I said that maybe in the problem-based learning, you're not given the threshold voltage, process variation, and all that, but it's an exercise to see if you can look up these typical numbers for that process technology from literature or from online, or maybe if you have access to this from your workplace, so you can use those typical values. Right? It's just to, because this is how we usually do it, right? Because sometimes these values are not there. You have to depend on people who have published some measurements on this. Because the standard deviation, the argument that you can use that is because the tools, the lithography tools are usually made by 2 or 3 companies in the world only. Mostly it's the same lithographic tools, so they probably achieve the same performance, that kind of thing. And maybe there may be slight differences in the actual value of the standard deviation, but it's not going to vary by too much. It'll be a good estimate if you can look it up on literature, what would be the typical process variation values like PTH variance, line edge roughness variance, oxide thickness variation. Right? So that'll be good for you to know, keep it handy, and to track as new processes are released. Yeah. Okay, great. So we've come to the conclusion. Any questions? Just pause. If you're fine, thumbs up. If you're not, think about it a little bit more. I can still take questions. Oh, okay, PBL. Yeah. Sorry, Felix, I've not updated the latest rubric yet. I'll be working on it, and I'll WhatsApp everyone once I've updated. Feel free to remind me again next week if it's not done. I'm just coming around to it, coming through a very busy period at the moment, so I apologize for that. Yeah. Due date for PBL. I think the due date should still be the same because the PBL one is just Okay, but I see what you're saying lah. You want to know how I'm going to grade it before you submit so that you know what you can put in. Yeah. I actually don't want to delay PBL1 by any further because it is already a lot of stuff is being delayed because it's just on the tools only. Okay, so I will maintain the 28th October, but I will try to get you the rubric as soon as possible lah. But the key fact is you should be able to just answer these questions directly lah. And then maybe with the rubric, you just fine tune your answers lah. So I'll justify the 28th October because I think it's really going to impact you all badly if I delay this one lah. Because again, the tutorials are already delayed, your test is delayed. PBL2 is still on track 26th November. You are crunching everything. You've got 2 tests, you're crunching everything into November if you keep pushing this back. It is not good, right? So I won't change the due date for PBL1 just for you to finish it up, but I'll try to get you the rubric out within the next 1 or 2 days. Okay, so you can just tweak your answers a little bit more, right? But the rubric is not a necessity for completing these. It's just if you want to really hammer in the answer, because the rubric is going to be something like, oh, got these kind of details, that kind of thing. But yeah, it's not going to stop you from answering these questions lah. Right, so please proceed to finish PBL1 at least by 28 October lah, because we're very delayed already. So I mean we're delayed a bit already. So I think it's really not great if we keep delaying it lah. Yes, Om Prakash, please go ahead.
Doctor, on the last section, I think got someone asked for the PBL1 extension, and you said yes, maybe we'll decide after the test.
Okay.
After
I
then.
said that. Okay.
Yeah.
Okay.
Maybe I think another week time will be fine for the
Are you
extension.
okay? I mean, because you have PBL1 and tutorial 1, tutorial 2 all coming around the same time, and then you have to schedule your test 1. If you're really okay with that, then I mean, I guess it's okay with me lah. I mean, if I promised you that, then I have to keep my word lah. Then it's fine lah.
I'm okay with that also, but we have to check with others.
Anybody really needs the PBL1 to be extended? Okay, maybe I give you a day or 2 to really argue it out in the WhatsApp group, because yeah, let me check. What did I say?
Doctor, for test 1, it will cover for PBL1, isn't it?
Yes,
For test
PBL1 and the timing estimation logical effort that from last session lah.
Okay.
Yeah. Om Prakash, I don't recall agreeing to extend PBL1. I only recall agreeing to postpone test 1.
Okay, Doctor, I have no problem. I just
Yeah, because I'm looking back at the messages. So I think PBL1 is actually not a difficult thing. It's just reading those 2 papers and going through tutorial 1 and all that, which I mean, I know you had something. Let's just take it to 28 October. And if you're really having challenges, you can PM me privately with your intended date of submission. If can still accept, okay lah. My goal is just to move you along lah, because if we are still stuck at PBL1, you're still not familiar with the process of VLSI, then it's pretty bad lah, because we have to schedule our test 1 pretty soon, and tutorial 1 and 2 should be due in the coming weeks already lah. So let's maintain the 28th October, but if you have dire difficulties, PM me your intended date of submission for assignment 1 lah, and I hope you can understand that I can't keep postponing the other assignments lah. And then the test is also coming already. All right.
Okay, Doctor. Thank you.
Okay, thanks for raising this one, Prakash. Yeah. Right. Any more questions? Okay, if no more questions, then we conclude for tonight. Thanks for your attention and the questions. And we'll be coordinating on the WhatsApp group on test 1 time. Huh? Okay. Right. Okay. So wish you all a good night and happy learning.
Okay. Okay. Good night. Thank you, Doctor.
Good night. Bye.
Thank you, Doctor.
Thanks.